because I think the Poisson community is quite diverse, so I thought I would just thoroughly introduce everything and not assume much besides the definition of a symplectic manifold. And so here's the outline of the talk. Before I talk about the outline, I just wanted to say that I'm attending so many of the seminars that I forget how it works here. I'm okay with anybody interrupting me for questions, but I will not see your messages in the chat. So if the host
if anything in the chat comes up,
tell
we'll
me.
tell it.
Okay, thank you. Right. Okay, so let's look at the outline. First, I will, as promised, I will introduce all the background necessary for understanding. So all the background that's necessary to introduce the moment maps. Then I will, well, namely the definition of symplectic geometry and all the Hamiltonian vector fields, Hamiltonian n-1 forms and all that. Then I will, the second part of the talk, I will talk about, I will introduce the observables, a very important notion. And then, so the nature, the flavor of these observables is very different in symplectic and emplectic geometry, although the emplectic case obviously generalizes the symplectic one. So this will take some time. And because the observables here form an object that may not be familiar to many people who don't work with this L-affinity category, I will also introduce the L-affinity algebras. And then finally, the third part of the talk, I will introduce the moment map, first in symplectic geometry, because I think it will give you more intuition of what it's about. And then in emplectic geometry, and then if time permits, I will compare two notions of moment maps in emplectic geometry, and this part of the talk will be based on joint work with Leonid Rivkin, who is I saw him in the audience. Hi there. Okay, so then let's start. Sorry. Right. So what is an emplectic manifold? An emplectic manifold is a manifold, smooth manifold, equipped with an n+1 form that is required to be closed. So the de Rham differential of the form vanishes, and non-degenerate in the following sense. So at every point of the manifold, if you look at the tangent space at that manifold and you plug in any vector from this tangent space into your form at that point, at point M. If you give 0, then that means your vector must be 0. So basically only zero vector fields contracted with omega give you zeros. And this is true at every point. Let's look at examples. So we'll start with the most familiar example, symplectic manifolds. So when n is 1, let's go back to this slide and see what happens. n1 means here we get a 2 form that is closed and non-degenerate, precisely the definition of a symplectic form. Other examples are orientable manifolds with a volume form. So volume form is a top dimensional form, so it's closed, and non-degenerate because it's a volume form. So the next class of examples, it generalizes the canonical canonical example of a symplectic manifold. So what's going on here? We take a wedge n of a cotangent bundle of our manifold, and then it turns out that this comes equipped with a canonical n form defined in the following way. So at every point, you take the form part and you put it here, and then you project these vector fields to the manifold. So this guy can eat these objects and give out a number. If you, just as I said, this generalizes the canonical example of a symplectic manifold, basically, namely the cotangent bundle of any manifold. And indeed, when n is 1, you just get a cotangent bundle here, and here you get the canonical tautological one form, or I think it's called Liouville form also. And then by taking the exterior derivative, I mean, the sign is up to conventions, but plus minus exterior derivative, you get the canonical symplectic structure on the cotangent bundle of a manifold. A slightly different example, different in flavor, is the following, but also very popular, is the following. So let's say you have a compact semi-simple Lie group. Then you can do the following thing. Your general Lie theory tells you that in this case, the G, the Lie algebra of G, has an ad-invariant inner product. So you can take the Mauro-Cartan form defined in the following way. Mauro-Cartan form takes a vector on any point in a tangent space of any point on G and like pulls it back to the identity, tangent space of the identity. So basically the Lie algebra. You can take the Lie bracket. You can apply Mauro-Cartan forms and take the Lie bracket right here and on G, and then apply this ad invariant inner product. The closedness here is due to this thing being invariant, and that follows from ad invariance. So it's closed because it's B invariant. And non-degeneracy is because of this semi-simplicity right here. Because this thing basically spans your G. Oh, sorry. Right. Okay. Now the next notion that's very important is the notion of Hamiltonian objects. So Hamiltonian n-1 forms and Hamiltonian vector fields. Let's look at the definition. So let's say we are on an emplectic manifold. Then an n-1 form on M is called Hamiltonian if there exists a vector field such that if you plug that vector field in your omega, you get the the derivative of alpha of the form. Then this vector field is called the Hamiltonian vector field corresponding to alpha. So since we assumed non-degeneracy, this vector field will be unique. And we will denote the set of Hamiltonian n-1 forms by this symbol right here. Let me tell you that if n is not 1, not all n-1 forms will be Hamiltonian. So this is not a void notation. With the notable exclusion of, so n equals 1, where we are in the symplectic case, and then your Hamiltonian n-1 forms are the smooth functions on M. And then because in this case, injectivity of the map, of this contraction map between the tangent space and cotangent space, bundles, will mean that it's an the injectivity will mean that it's an isomorphism, and then every f, for every f, you can get a vector field that satisfies this. So in that case, any function has a unique corresponding Hamiltonian vector field. All right. So we pass to the observables now. And should I say this now or later? Okay, so before I say this, it will be because this will kind of explain where the word observables comes from. So the thing is, as you probably know, symplectic geometry has its origins in the Hamiltonian mechanics. So in the Hamiltonian formulation of the classical mechanics. And this word observables comes from there. So observables are things that you can measure on your manifold, and functions are precisely something that gives you a numerical value at every point. And n-plectic geometry, n-plectic manifolds, they come from the generalization of, sorry, not generalization, I'm sorry, the mathematical description of classical field theory. So symplectic geometry describes classical mechanics, n-plectic geometry describes classical field theory. Okay, right, and now I tell you what the Poisson algebra of observables is, but you you know this already. So let's M be a symplectic manifold. Then the Poisson algebra of observables on M is as the underlying vector space has the smooth functions on M, and the bracket, the Lie brackets, the Poisson bracket is given by the following. So for F and G, you just take their corresponding Hamiltonian vector fields and you contract them into your symplectic form. All right. Right. Okay. Now what to do? Now we want to we want to introduce, or well, first define an analogous structure on for corresponding to an m-plectic manifold. So let's say we had a Lie algebra. I will warn you that while this object is indeed a Poisson algebra, so there's also commutative algebra structure here, and it's compatible with the bracket. I will not be interested in that commutative algebra structure from now on. I will only be interested in the Lie algebra structure. So what I want to do is I want to find a Lie algebra that corresponds in a natural way to my m-plectic manifold. And what I can do, I mean, not people before me try to do, they they try to just imitate the procedure that of the symplectic geometry, right? So if here we had C infinity M, so 0 forms, then the natural candidate in n-plectic geometry would be Hamiltonian n-1 forms. And we can also define a bracket in this way, just like we defined it here. And that almost works. So what works is that you end up in the Hamiltonian vector fields, but sorry, not vector fields, n-1 forms. So if you a bracket of 2 Hamiltonian n-1 forms is a Hamiltonian n-1 form again, due to this identity here. And you also have the skew symmetry. What does not work, however, is the Jacobi identity, because if you try to calculate this thing, it's almost there, but it's an exact element instead of a 0. So what to do? I mean, what I will talk about one way of going about this, but other people before this whole L-infinity business was introduced in this framework, what they did, they just considered forms modulo exact terms. But we will not do this here because we have a very nice framework to just incorporate all of this and still get a nice structure. So teaser, L-infinity algebras will save us. But first, let us introduce L-infinity algebras. So, well, people who introduced them claim that the idea has been floating around unofficially, sort of. But I mean, officially, this structure was introduced by Lada Stashev. So. L-infinity algebra, according to them, is a graded vector space equipped with a collection of brackets. So let's go slowly here. We have a graded vector space L, and we have a collection potentially arbitrary number of graded skew-symmetric multilinear maps. And what happens is that, so each of these maps, so if I'm indexed by 1, for example, the first map indexed by 1 takes one element and has degree 2 minus 1, 1, right? Then the second map takes 2 elements and has degree 0. The third map takes 3 elements and has degree minus 1, and so on. And they are required to satisfy so-called higher Jacobi identities. I did not put them here because they are not very, they're enormous, and maybe they're not immediately telling you very much. But I will decode the first 3 of those higher Jacobi identities. So the first one tells you that your first map squares to 0, and we already said that it was of degree 1, so it's a differential, and thus an L-infinity algebra is also in particular a cochain complex. We will, from now on, because this is a differential, we will just denote this first map by D. Okay. The second one of those Jacobi identities tells you that D is a graded derivation of the second multi-bracket. So the second map, this is the second map from this list. And the probably maybe the one that's this, well, maybe I shouldn't say that. So the third identity tells you the following, that the following thing holds. But what do you see here? If you just look at this, the left-hand side here, you will see the left-hand side of the Jacobi identity of Lie algebras. But on the right-hand side, you will not see 0. And remember, we faced this problem while when we tried to generalize the bracket structure to emplectic geometry. But what do you have on the right-hand side? You have this. And in particular, if you take x, y, and z such that they are in the kernel of the first map of D, what you will get is that your Jacobi identity is satisfied up to an exact element. In the language of homological algebra, this is referred to as up to homotopy. So you often hear that the Jacobi identity is satisfied up to homotopy. And this explains the second, so this paper where Lada Stashev introduced these objects, it was called, I think, an introduction to strong homotopy Lie algebras. So these objects were called strong homotopy Lie algebras. So this up to homotopy business is where that name comes from. So let's give examples. What are the familiar examples of L-infinity algebras? It turns out that these are the very nice familiar objects. For example, cochain complex, because we already saw that the first map is at differential, sorry. And second example, a bit more involved, a differential graded Lie algebra. And this happens if we take just any a differential, the second multi-bracket, and we take the third multi-bracket to be 0. Then, just as we said, remember the second one of these Jacobi identities told us that D is a graded derivation of the binary bracket. So precisely this. And then this guy being 0. Oh, I'm sorry, makes all these guys disappear on the right-hand side. And then we have a nice graded Jacobi identity for ourselves. And here's the Leibniz identity. So we have a differential graded Lie algebra. And the Lie algebra case is covered by just taking L to be a non-graded, just an ordinary vector space. And, oh, sorry, typo. This has to be D. So if D is 0, well, it becomes a Lie algebra, just a Lie algebra. Do we really need that actually? Well, yeah, well, D will be 0 automatically because we don't have anything else. Okay, right. Okay, so there is an alternative description of our L-infinity algebras. Let me, how am I doing by time? Okay. There is an alternative description of our L-infinity algebras, and this description is useful because it's more conceptual and it allows us to formulate a conceptual definition of an L-infinity morphism. So of a morphism between two such objects, two L-infinity algebras. It turns out that there is a way to cook up a differential graded coalgebra out of this data, so out of the L-infinity algebra, so the vector space and the multi-brackets. And then, so this object will be a differential graded coalgebra. And then those enormous, unpretty, if I may say, higher Jacobi identities will be equivalent to just this simple, elegant D squares to 0. And this also lets us define a morphism of two L-infinity algebras, and namely we define it as a morphism of objects of this kind. So so a coalgebra morphism of graded coalgebras that intertwines the differential. I'm sorry, I got a message that my internet connection is unstable. Did you miss any part of what I said?
No, it's perfectly fine.
Okay.
Once in a while you slow down a tiny bit, but it's not a problem.
Okay, thank you. Right. So so it's a coalgebra morphism that intertwines the differentials, the respective differentials right here. And I'll just tell you that the differentials are just cooked up from these brackets. There's nothing else, not much more. There's just some sign magic going on. Right. As I said, this is a conceptual, nice, compact definition. But to do calculations sometimes, or for proofs, we need to translate this into something more tangible, to something more concrete, if I may say that. So this also translates into the following. So a morphism between two L-infinity algebras corresponds to a collection of graded skew-symmetric maps from that like this. So each is from the k-fold tensor product of L to L prime. And the degree of each map is 1 minus k. So again, the first map is degree 0 and so on. And that are in some sense compatible with the brackets. This is a clumsy expression, the one that expresses this compatibility, but for the first map, it's easy. It says that the first map has degree 0 and is a chain map. So intertwines the first brackets, the differentials of these objects, okay? Yeah, and in the other cases that we will be interested in, I will give you what it precisely means. Okay. Right. So, and why were we doing all this? Why do we need infinity algebras? Well, to associate a nice object to an n-plectic manifold. So it turns out Chris Rogers discovered that if you have an n-plectic manifold, you can there is an L-infinity algebra structure, an L-infinity algebra associated to your n-plectic manifold, and as the underlying vector space, it has the direct sum of C infinity m omega the one forms and so on up to up to n-1 Hamiltonian n-1 forms. And as I think this is not necessary, but we take this guy to be in degree 0. Right, no, this is, sorry, ignore what I said. So this guy is in degree 0, and then it goes by decreasing degree by 1, and then the final, the C infinity M is in degree 1 minus n. And the following maps, because as we know, the L infinity algebra is the vector space and the collection of maps. And these maps are they're not very bad, because they're only non-zero if all your components live in this space right here. So here. And if all of them are here, in that case, this is how the multi-bracket is given. The case multi-bracket is given by after sign contraction of the Hamiltonian vector fields corresponding to these n-1 forms. This looks a bit maybe intimidating, so let's see what happens for lower n's. For n1, we just get zero Hamiltonian 0 forms, so C infinity M, and the only multi-bracket that survives is the second one, and it's given so the binary bracket, and it's given by this. So we just recover the familiar Poisson algebra of observables. But again, I will have to remind you that we're not interested in the commutative algebra structure. Right, and a slightly less, well, I don't want to say trivial, but a slightly more involved maybe example is a two-plectic manifold that has, now we have two terms in the L infinity algebra, so Hamiltonian 1 forms and the smooth functions on M, and the first map, the differential, is just the de Rham differential, and there are two multi-brackets now, the binary bracket given by this and the ternary bracket. All right, okay, right. So now that we have the L infinity algebra of observables, we can go on to define moment maps. So I will start from the symplectic moment map. You probably remember this, but I just want to remind you and make it consistent with the definition of homotopy moment map that I will introduce later. So we are also interested in the so-called, this is actually a co-moment map if you are very precise, because we're interested in the Lie algebra morphism from the algebra of symmetries into the Poisson algebra of observables. But let me tell you what the definition is. So we have assumed the setup is the following. We have a Lie algebra acting on M. Usually you say that it acts by symmetries, so it acts by the preserving omega, but the thing is, this guy already, the fact that we require this already implies that, so I didn't put it here, but yeah. So we have a Lie algebra acting on M, and consider the Vx to be the infinitesimal generator of the action corresponding to an arbitrary element of this Lie algebra. Then a co-moment map, which I will just call moment map, for G is a Lie algebra morphism from G to this Poisson algebra of observables, such that this Hamiltonian condition is satisfied. So what it means is, if you remember, a Lie algebra action on the manifold is just a Lie algebra morphism from the Lie algebra itself into the vector fields, and we want a lift of this morphism. So the lift of this Lie algebra morphism is the moment map. Okay. As for interpretation and applications, I really like this way of saying it. I mean, probably it is not, there's nothing extraordinary about this. You probably all realize this, but the fact that this is phrased in this way, I really like it. So the beauty of the moment map is that it enables to relate the geometry of symplectic manifold with symmetry, symplectic manifold with symmetry to the structure of its symmetry group. So it relates the symmetries on the symplectic manifold to the geometry of the symplectic manifold. I stole this from Nicholas Woodhouse. Now, the applications of the moment map are ample, actually, and I just list the following four. So Noether's theorem, Hamiltonian version of the Noether's theorem, it says that for every x in G, if you take the image of any element of a Lie algebra under this moment map, then it will be conserved. And conserved means that it will be conserved under the evolution of your system. And conserved in this case means that the Lie derivative with respect to the Hamiltonian vector field of the chosen Hamiltonian will be 0, but I did not introduce any Hamiltonian, so maybe I should not have said this. Right. The next application, quite I would say connected to the first, is symplectic reduction, and so it's the celebrated Marsden-Weisner theorem, and in particular, this infinite dimensional version. Sort of the Atiyah-Bott construction, so the moduli spaces of gauge theories. Another application is the classification of toric manifolds. And so with this Delzant polytopes, if it tells you anything. And the representation theory, by this I mean this constant Surreal orbit business, where you can sometimes, for some Lie groups, you can have a bijective correspondence between the coadjoint orbits of G. So the coadjoint, the orbits under the action of G on the G star, sorry, the group G, and the G star is the dual of the Lie algebra. And on the right-hand side of the correspondence, the irreducible unitary representations of G, of the group G. So this is apparently important in quantization, but I don't know much about that, unfortunately. Okay, now it's time to define the homotopy moment map. So a moment map in emplectic geometry. So this is very analogous to the definition on this slide. It's just that the objects changed accordingly because we are in emplectic geometry. So what we have here is that, again, we have an action of a Lie algebra on an emplectic manifold. I required by Hamiltonian vector fields, but this is a bit redundant since I already say this in here. That a homotopy moment map for this action is an L-infinity morphism. Disregard this for a moment. So it's an L-infinity morphism between G and this L-infinity algebra of observables, the one from this slide. All right. Such that the following holds, but before I should tell you what this means. Remember when I told you that L-infinity morphisms are morphisms between this differential graded coalgebras. I will now go back to that slide. I also told you that it translates to a collection of maps. So here we abuse the notation or terminology and equate the morphism with its corresponding collection of maps. So here, this is our L-infinity morphism between these two L-infinity algebras, and it's a collection of maps such that the first one of these maps satisfies the following. So basically, the first one maps an element of Lie algebra to a Hamiltonian n-1 form corresponding to Vx, so infinitesimal generator of the action that corresponds to that element. And again, at the sort of a direct generalization, what we have generalization of the symplectic moment map in the sense that again we have this action, the Lie algebra morphism. So a Lie algebra morphism is also an L-infinity algebra morphism, and then we choose to lift it in this L-infinity category. So that's basically what happens. Right. So this is why I wanted to remind you of what a homotopy, of what a symplectic moment map was, so that you see the direct analogy. Okay, but all of this is nice and conceptual, but again, to work with proofs, I guess we need a bit more detail. So I will write what it means precisely for these components of the F. First, let me remind you of this case Lie algebra homology differential. So basically the dual of the Chevalier-Eilenberg differential, that's more well known maybe. And then a homotopy moment map for an action of G on an epileptic manifold is a collection of n linear maps. So linear maps from wedge k of G into the n minus k forms on M. So there are n maps and they satisfy n+1 equations like this. And the so where by F0, because if you plug, for example, 1 here, you will get an F0 here, but F0 we take to be 0, and so the same for n+1, because if you plug n+1, still here you will get n, and then this guy will matter, but if we take it to be 0, then everything's fine. Yes.
Lela.
Yes.
Lela, what does the zeta mean?
I'm sorry.
In your formula.
Yes.
There's zeta k times I.
Oh, what is zeta k? Yes, thank you. Yes, I did not write that. Right, it's a sign. It's if I'm not mistaken, it's -1 to the power k times k+1 divided by 2, and then another minus before that. It's a sign.
Thank you.
Is that okay? Yeah, sure. Yeah, sorry about that. Should have written this. Okay. Right. And before I go any further, I would like to discuss a little bit of which applications of symplectic moment maps kind of carry over. And let's go back to that symplectic applications, well, symplectic moment map applications slide. We had 4 here. So let's start with the first Noether's theorem, Hamiltonian version. It does have, so a homotopy moment map does provide a version of a Noether's theorem too. But I think possibly one of the caveats would be that in epileptic geometry, a lot of people do it sort of differently. And if you see the Noether's theorem that in other people's works, it can be slightly different because the framework is slightly different. But I'm not entirely sure if they're all directly precisely equivalent. I wanted, actually that was on my list to check, but just to warn you that different people may do multisymplectic geometry differently. So the formulation of this Nutter's theorem can be different as well. But it does hold. So a homotopy moment map does admit a Nutter's theorem. Then symplectic reduction, that's the first one that stops being so symplectic reduction in full generality as Marston-Weinstein result, it doesn't hold, but it holds for special classes of emplectic manifolds. And in particular, it holds for moduli spaces of flat connections. So if you're interested in that result, it's in the paper by Marco Zamon. Sorry, it's not in alphabetical order. Martin Callis, Yael Freger, Chris Rogers, and Marco Zambon. I just said Marco first because he's my supervisor. Right. And the following two, this result that I really like, I don't know if there's anything like that. I was interested in, so Marco and I were kind of interested in exploring this, but we didn't go very far. And this one, I'm not even sure if that question would make sense. Oh no, it would make sense, but I don't know if anything can be said about this. So long story short, the first two kind of hold, generalize. The last two, I don't know. Okay. There are also other applications of homotopy moment maps. So there are applications to loop spaces, but because I don't know very much about that, I didn't want to say anything wrong. Okay. But again, you can check it all in that paper where they were all defined. It will be in the bibliography. Right. So it's good. We have still 13 minutes, and I think I can manage to say something in the 13 minutes about the other homotopy moment map.
You can take a bit more time if you want.
Okay. Okay. Thank you. Yeah.
We started 5 minutes late, and we're very flexible.
Right. Yeah, that's also true. Okay, right. So let's. So here's the other moment map in emplectic geometry that I wanted to tell you about. So let's first start from the definition, and then I'll tell you something a bit more. So again, the setting is the same. Lie algebra acting on an emplectic manifold. A weak moment map, it's also it's kind of a homotopy object, so it's a weak homotopy moment map. It's a collection of linear maps from this space right here into into the forms, differential forms on the manifold. And again, we have precisely n maps, and they satisfy the following equation with this set k again is a sign that it's just a sign. Let's pause a little bit and see what's going on here. First of all, what are these PKGs? They are the kernels of this guy right here, of each delta k. So each PKG is the kernel of the kth Lie homology differential. So what you see is that the domain of the weak moment map is a subspace of the domain of the strong, let's say strong homotopy moment map. Because here we had maps from delta k, so not delta k, I'm sorry, wedge k of G. And here we have maps from a subspace of that. And they are required to satisfy the following equation. Should I say this now? No, I will say right away. So they were introduced by Jonathan Herman, and his motivation in introducing them was also emplectic Noether's theorem. And probably his motivation was a bit more physicsy, but he's a mathematician. and the generalization of the classical position and momentum functions to symplectic geometry. So what about this Noether's theorem right here? The thing is, as I told you, the weak moment map is okay. So let's say the following. So the weak moment map, as I said, is the domains are the restrictions of the domains of the strong homotopy moment map. And what do we see? We see here that if we plug in those kernels of this guy, so the domains of the weak moment map, this guy here will disappear. So we precisely get the this. What it tells you is that the homotopy moment map restricted to the kernel of the delta case is a weak moment map. But because the motivation of Jonathan Herman was symplectic Noether's theorem, and it is true that to get the symplectic Noether's theorem with homotopy moment, with a strong moment map, you don't need you really do need to restrict to this Lie kernels. That was the result in the paper by Marco Zambon. Again, I'm sorry, I said his name first. So it should be Rifkin, Zambon, Wurzbacher. The conserved quantities in multisymplectic geometry, if I'm not mistaken, that's the title. They have this result that the components of a homotopy moment map restricted to the Lie kernel give you conserved quantities. And then what Jonathan Herman did, he just took this restriction of a homotopy moment map, and then he realized that he doesn't need anything else, and he can actually strengthen this result by giving a one-to-one correspondence between symmetries, just like in Noether's theorem. So symmetries give conserved quantities and vice versa, and he got a similar result for, in this case, using just the weak homotopy moment map.
Sorry,
so
can I ask you something?
Yes. Yes, of course, yes.
Which is the simplest example of weak homotopy moment map which does not come from by
Very
restricting
good.
the homotopy?
Thank you. A simplest example of a weak homotopy moment map is already in, I would say, in the symplectic geometry. Because in the symplectic geometry, this means that you have just a non-equivariant moment map. So let's say you are in a, you have a Lie algebra for which the first cohomology, Lie algebra cohomology vanishes, and let's say you have an equivariant moment map for that, and then you just alter it by the moment map by adding an element, adding a constant. And this amounts to adding an element in to the dual, adding an element in G star, but because your first cohomology vanishes, of your Lie algebra vanishes, that if you have an equivariant moment map, it's unique. So the new one you got is not an equivariant moment map anymore. It's a weak map, and it doesn't come from any equivariant moment map, because the restriction in the first one is just the G itself. So the kernel is the full thing, all of G. Does this make sense?
Sure.
Sorry. Yeah.
But in that case, somehow it's about the action that you consider of the group on the dual of the Lie algebra. I mean, even if the moment map is not equivariant, you can change the action to an affine action and make it equivariant. So in some sense, any moment map is equivariant.
You mean an action from this extension, or?
Yeah. Let me try to reformulate the question a bit more concise later on.
Okay, sure. Yeah.
Just go ahead.
Yeah, because actually the stuff that I was going to talk about next, it deals with this question too. Right, so we have these two moment maps, and what Leonid and I were wondering is, I said every homotopy moment map restricts to a weak moment map, but is the converse true? If you have a weak moment map, do you always have a homotopy moment map? Let me first tell you that this question kind of hides two questions inside it. First of all, if there is a weak moment map, is there always a homotopy moment map? And another question is there a homotopy moment map that restricts to this weak moment map? And these two questions have different answers. So first, the first question is, let me just quickly see if I have, how much time can I still have, like extra 10 minutes or 5 minutes? Sorry?
Mari says it depends on how much you're willing to pay.
Oh.
No, take whatever you need.
Okay, thank you. So, right. So let me just say ahead that the first question, if there's a weak moment map, is there a homotopy moment map? That one has a slightly easier answer, because if we just have to add one extra assumption, and then the answer is affirmative. So to prove this, maybe I shouldn't. So let me do the following. I will not tell you much about the proof, maybe, but I will first show you this theorem that Leonid and I obtained. So if there's an epileptic manifold and G acts on it by preserving omega, then the following two are equivalent. So basically, if there's a weak moment map and plus a certain phi that is defined in the following way vanishes, then there is a homotopy moment map. The second question, however, was, sorry. The second question was, here I talk about the proof. I will go back to it later. So the second question was, if there's a weak moment map, is there always a homotopy moment map? Sorry, if there is if there's a weak moment map and this extra condition is satisfied, because in that case there is a homotopy moment map. And also I have to tell you that if this condition is not satisfied, there is no chance that you have a homotopy moment map. Just doesn't. So this is necessary as well. Does there exist a homotopy moment map that exists to a given weak moment map? And the answer is, if the certain class in a certain complex vanishes and has a primitive in a certain space. So this is not very, not as concise as the first existence result. And to explain what these classes are, I will just go back to this slide and tell you a little bit about what's happening. So we consider two double complexes. The first one is kind of, in air quotes, a tensor product of the Chevalley-Eilenberg complex with the de Rham complex, and we consider the total complex of that. And then the second one, in the second one, we consider a similar tensor product, but this time we're tensoring with this guy right here. And what it is just the direct sum of all these duals of all those pKs, so all those Lie kernels. And this one also has this a total differential. We will denote this one by C hat, this one by C tilde. Then it was a result of these two papers independently appeared about the same time. That's a homotopy moment map. So the strong moment map exists if and only if a class of a certain element in this first complex vanishes. And this element is just cooked up from the action and the omega, so the n+1 form. There's nothing else to it. And then Leon and I, we realized that a similar thing is true for the weak moment map. So in this complex, in the second complex, we can also define a very similar omega hat that's also cooked up from the action and the form. It's basically just a restriction of this to the Lie kernels, modulo one little thing. Yes, and a similar result is true here. If and only there is a weak moment map, if and only if this class vanishes in this second complex. Right. So this I told you about. So just to a sketch of the proof, basically what we did was construct a map from the n+1 cohomology of the first complex into the n+1 cohomology of the second complex, and if we could show that this map was injective, then this thing vanishing would imply this thing vanishing, and then we would get because of these two results, we would get that if a weak moment map exists, then also does a homotopy moment map. And indeed, that's what we did, just by considering this exact sequence and then noticing that the dual one is exact, and noticing that this implies the following inclusion. And basically just applying the Kunet formula. I mean, I'm saying basically just doing this, but it involved quite a bit of construction to make things work. Right, but these are the big sketches in the proof. Right, and now as for this question is, so again, you see that this class is in the first complex. But we don't just need it to vanish, but we need it to have a primitive in this subspace right here. And all of this is well defined, independent of the choice of representative and all that. Okay, so I think good. Wow, I made it in time. Yeah, I'd be happy to hear your questions. Thank you. Did I miss something? No. Oh, thank you. Thanks. Yes.
Unmuted, yeah.
Are there any questions?
Marius, maybe you should say this.
Hmm?
Maybe ask if this.
Questions? So these double complexes, are they related to equivariant cohomology or not?
So which one? Yeah. So I think yes. So the thing is, this homotopy moment map. I don't know about the second double complex, but because this was inspired by the first one, so I will just say that yes, this complex in the paper. This paper that I cited by Marco and three other people, where the homotopy moment map was introduced, they explored the existence of homotopy moment map in terms of equivariant cohomology, and this the result from symplectic geometry that it exists if a certain element is closed in this equivariant, well, in a certain complex, that carries over. And yes, it's very similar in flavor. It was a bit weird because when I so yeah, long story short, yes, it does. It is related. It was mainly the inspiration, I think. I never maybe Leonid because he was him and Tilman Wurzbacher, they published their paper about the same time. They can maybe also he can tell us whether the inspiration was equivariant cohomology, but I think it was. Sorry, do you hear me?
Yeah, Leonid had to board a plane. So.
Oh, Leonid had to board a plane, it seems.
Oh, yeah, yeah. That's fine. So I if I may, I will say yes.
Okay.
Do you have a list of
Yeah.
Sorry, do you have a list of references?
Oh yes, I do. I'm so sorry. Yes, right here. So there are two pages of references. All of the ones that I mentioned are all here. And I will upload the slides, right? I think we upload the slides.
Thank you.
Yeah, sure. Thank you.
You had this nice list of examples of
Yes.
emplectic structures.
Right. Yes. Let me go back to that.
There was, for instance, this cute one with the Cartan 3 form on
right.
a
Yes.
semi-simple E group or the volume form.
Yes.
What does this result of yours become in such examples?
Ah, right. That's a good point. So as far I think, let me think. So I think if so, this group is acting on itself by translations, and if we have right, yeah, very good. So if the group G is acting on itself by translations, then actually there is a weak moment map, but not a homotopy moment map. So that's
and the weak moment map, is it clear?
Yeah.
The weak moment map.
Is it clear? Let me think. So you mean the explicit components?
Yeah.
Let me think. I think I haven't thought about that. I know it exists because of cohomology things. So
I see.
For cohomology reasons on the group on the Lie algebra cohomology, but I'm not sure. I think no, I don't think I can like from the top of my head say what explicitly the components are.
Okay, but now I'm just wondering, I'm getting more curious because of this example with G. I mean, this example with the Cartan form makes you think about these other moment maps, which are Lie group valued moment maps. Is there a version of Lie group valued moment maps up to homotopy?
I don't know that, unfortunately. I was actually, so my big goal was to look at all the existent examples of moment maps in the literature, which are different not only in terms of the codomain, but also domain, and kind of see if there is any, you know, if I can make a map from you know, between these, but I not thought about that yet, unfortunately, not the ones with group valued, but that's an interesting question.
Yeah, there are lots of questions. It's another one is like, because it's Friday fish, it's
right.
I mean, you already mentioned symplectic reduction. Symplectic reduction, okay, you have this reduced symplectic quotients, right? But the big picture is really a quotient modulo the group, which has a Poisson structure, and the symplectic leaves are the symplectic reductions.
Yes.
So what's the analog of that, and what's the analog? How is Poisson? I mean, and fishic, or how do you call it?
Yes, so some kind of an N Poisson structure. Unfortunately, also, so I when I got the email about coming to speak here, I told Alvaro that, you know, this is not really Poisson geometry except in n equals 1, but unfortunately, I'm not aware of any similar results. So I mean, something that's
well, I think the question is not, the question is really not to imitate, but like if you think about symplectic reductions, to think about in cases when it works, to think about it like being part of a big picture. Like in the classical case, these are just symplectic leaves of Poisson structures, right? So it's one can try to play the same game and then discover what the Poisson analog is, because otherwise it looks a bit artificial.
So I think, yeah. So in those cases where we have a multisymplectic reduction, yes, that would be interesting to. But as for it being a bit artificial, I mean, it probably depends a little bit on the point of view, because when these things started, they didn't start as a search for Poisson structure and the symplectic leaves. Yeah, I don't. That's definitely a great question to look
But when
into.
I said artificial, I was thinking about a game in which you say, okay, let's think about n vectors now and imitate the same story. So that would look a bit artificial. Maybe it leads to something, I don't know, but.
Yeah, so sometimes I think, yeah, that's true. But what I noted is that sometimes you work from kind of top to bottom and sometimes from bottom to top. But maybe,
But maybe an idea to go in the direction is this point of view on Poisson structures and on symplectic structures as well, via Dirac geometry, right? Which Dirac geometry allows you to, and you interpret your objects like via the graph, and then you include more examples. Did anyone try to embed this into a Dirac type of geometry?
Yes, Marco did. I think Marco did. There was an attempt. Unfortunately, I don't precisely remember the result, like the precise result. But let me just. I mean.
Also, Marco's boarding a plane or what?
No, Marco is not. Probably he's not here. Just a second. Yeah, I can only remember the title of the paper by Googling it, if you don't mind, but you will see me Googling. Let's just do that.
Yeah, Antonio put it on the chat.
Sorry?
Antonio put it on the chat.
Antonio did. Okay, very good. Thank you. Thank you. Yeah.
Okay.
So there is this is all, I mean, relatively, I don't know what's new nowadays, but I think this is all relatively new, and a lot of people are working on a lot of things, not necessarily all connected, but maybe in a I don't know, in a decade there's a tapestry where all of these little mosaics are connected. I don't know. Hopefully.
I think other people should ask questions. Okay, thanks.
Thank you.
More questions? Aldo, you are the boss.
Sorry?
Yeah, maybe let's read Ivan's question.
Well, somebody's saying that there is a question by Ivan.
Sure.
Ivan, speak up.
Not really a question. Well, it could be a question, but I was trying to go in the direction that you were asking. If you couldn't consider, for example, like multiplicative n-plectic groupoids to try to understand what the structure of the base is and see what the Poisson analog of these structures are.
Multiplicative n-plectic groupoids.
If I'm not mistaken, Henrique Burstein looked at something like this. I'm not sure.
Sorry, I don't hear very well. Can you? Who were the authors?
Henrique Burstein.
I think with Alejandro Cabrera probably.
Ah, yeah. Okay, Henrik Burstein. Yeah, Henrik Burstein. Okay. Okay, yeah, maybe that's all. That's all.
That's a good point.
Mari says it's a good point.
Yeah.
Thanks for the talk, by the way.
Thank you for listening. Yeah, I never know. I mean, how like slowly to go, but I just assumed that the audience, not everyone in the audience was familiar with the objects. So I hope it wasn't too boring.
That's fine.
Thank you very much.
It would have been great to have your talk before the multisymplectic workshop of 2 weeks ago. To help understand the other two.
Oh yeah, yeah, probably. Yeah, that's true. I'm a bit. I always wonder if sometimes the talks are too fast, and I wonder, like, maybe we would gain more by maybe not telling about all our results, but first introducing people to the framework, because this is not a very widely adopted framework.
Yeah. No, I appreciate it a lot that you explained.
Thank you. Yeah. Thanks.
No more. If there are no more questions, then let's thank Leyli again.
I think Rayer wanted to ask.
Or
what? We're good.
Okay.
Thank you.
I think Rayer, he was unmuted, so I assume.
Rayer, did you want to ask a question?
No, I'm done. Thank you very much. Thank Leyli.
Thank you. Thank you.
Yeah, thanks,
Thank you for
Leyli.
great questions that inspired me to look into some things. I made notes. Thank you.